You're sitting in your seat, the plane is pushed back from the gate. You hear that familiar whine start to build outside your window, and within a minute, you're taxiing toward the runway. Most people don't give it a second thought, but I want to tell you what's actually happening right outside that window before you ever hear that sound, because almost nobody knows. That engine cannot start itself, not even a little bit. What you're about to hear is not an engine starting on its own. It's an engine being forced into existence by a machine sitting on the ground that most passengers walk right past without ever noticing. That machine has a name. It's called an air start unit. You've seen it before, even if you didn't know what you were looking at. It's that boxy cart, usually painted yellow, sitting right beneath the wing with a large flexible hose running up into the engine cowling. Ground crews move around it like it's just part of the furniture. Pilots depend on it completely, and the average traveler has no idea it exists. Understanding what it actually does changes how you'll experience every departure for the rest of your life. To understand why it's needed, you have to understand what a jet engine actually is. At its core, a jet engine works on 4 actions happening in rapid sequence. Air comes in the front, it gets compressed, fuel gets injected and ignited, and the exhaust blasts out the back, pushing the aircraft forward. Simple enough, but here's the catch. That compression stage, the part that squeezes the incoming air tight enough for ignition to even be possible, needs to already be spinning at high speed before any of this can work. We're talking thousands of revolutions per minute, and the engine has absolutely no way to get itself there from a dead stop. It is, mechanically speaking, a machine that cannot wake itself up. That's where the air start unit comes in. It forces the issue. The cart contains a heavy-duty compressor driven either by a diesel engine or in newer units by electric power, and it pumps air at extreme pressure through that hose directly into a starter motor connected to the engine's turbine shaft. We're talking pressures in the range of 30 to 50 pounds per square inch. That airflow isn't gentle. If you were standing in the wrong position near that connection point during a start, it would knock you off your feet. Inside the engine, turbine blades that weigh several pounds each are being driven from a complete standstill to thousands of revolutions per minute in a matter of seconds. The whole process is, without exaggeration, a controlled detonation. The engine doesn't ease into operation. It gets blasted there. Now, here's where it gets really interesting, and honestly, where the margin for error gets razor thin. There is a very specific speed window during start where everything has to come together. The turbine shaft has to reach a certain rotational speed before fuel can be introduced and the igniters fired. Too slow and fuel enters the combustion chamber without burning properly. It pools, it accumulates. When ignition finally catches, it catches hard, and exhaust gas temperatures spike so fast the instruments can barely track it. That's called a hot start. Too fast, on the other hand, and you've burned through your compressed air supply without achieving a clean light off, and you're starting the sequence over. The flight crew sits in the cockpit watching 2 specific gauges during this whole process, tracking the N1 and N2 shaft speeds, waiting for the exact moment to introduce fuel. Miss the window and the start has to be aborted. There are 3 specific failure modes that every crew is trained to recognize and respond to, and all 3 of them can cause serious damage in a very short amount of time. The first is that hot start we just described, where temperatures blow past limits before the engine stabilizes. The second is what's called a hung start, where the engine lights off successfully, but then simply refuses to accelerate any further. It sits at a low RPM with fuel burning and heat building and nowhere to go. Like a car engine that cranks but won't rev, and left unchecked, the heat will destroy the turbine components. The third is a compressor stall, where the airflow inside the engine reverses direction suddenly and violently. If you've ever been near a jet engine during a compressor stall, you don't forget it. There's a loud, deep bang that echoes across the whole ramp. Everyone stops. All three of these scenarios can go from manageable to catastrophic in seconds. Feel free to subscribe if this aviation interests you. Let's talk about what that actually costs. A modern high bypass turbofan engine, the kind hanging under the wings of most commercial jets flying in the United States today, is worth somewhere between $15 million and $40 million, depending on the model and configuration. A botched start that causes a hot start or a compressor stall doesn't just mean a delay. It can mean mandatory hot section inspection, which involves partially disassembling the engine to examine the turbine blades and combustion components for heat damage. It can mean blade replacement. In severe cases, it means the engine comes off the wing entirely and goes back to a maintenance facility for full overhaul. That's an aircraft on the ground for days or weeks. The costs can run into the hundreds of thousands of dollars, all traceable back to a start sequence that lasted less than 90 seconds. The air start unit itself is not expensive either. A standard diesel-powered unit runs between $80,000 and $180,000 new. High-output electric models used at major hub airports can push past $250,000. And airports don't operate one of these. They operate fleets of them. Every gate, every aircraft turn, every engine that needs to be started cold depends on one of these units being available, functional, and properly connected. Factor in maintenance contracts, diesel fuel consumption, and the downstream cost of a cart failure causing a departure delay during a peak travel period. And the economics of ground support equipment become something airlines and airport operators think about very seriously. At this point, you might be asking a reasonable question. Don't planes have their own built-in system for this? And the answer is yes, partially. Most commercial aircraft are equipped with what's called an auxiliary power unit, typically located in the tail of the aircraft. The APU runs on jet fuel, generates electrical power, and can produce compressed air for engine starts. When you're sitting at the gate and you hear a higher pitched whine before the main engine start, that's usually the APU running. But APUs have real limits. They aren't designed for continuous operation. They burn fuel, which costs money. They produce noise and emissions while the aircraft is sitting at the gate. And in certain conditions, including hot days, high altitude airports, and situations where the APU itself is out of service, the APU simply cannot produce enough pneumatic pressure to get the main engines turning. In those cases, the air start unit is not a backup option. It's the only option. Here's one more piece of this that most people never learn. On a twin engine or four engine aircraft, you don't necessarily need an air start unit for every engine. Once the first engine is running under its own power, it's possible to route compressed air from that running engine through the aircraft's pneumatic system to start the remaining engines. This is called a cross-bleed start. The first engine, which itself was started by the cart sitting on the ramp below you, essentially becomes the starter motor for everything else. One cart, one engine, and then a chain reaction that brings the whole aircraft to life. Airlines use cross-bleed starts regularly at busy airports to reduce their dependence on ground equipment and speed up the turnaround process. Now, it's worth mentioning where all of this is heading. The newest generation of commercial aircraft, including the Boeing 787 and the Airbus A350, have moved away from pneumatic engine starting entirely. These aircraft use electric motor generators built directly into the engine to drive the turbine shaft up to ignition speed using electrical current rather than compressed air. No cart, no hose, no 50-pound per square inch air blast, just electrical power from the ground or from onboard systems, spinning the engine up cleanly and quietly. It's a significant engineering shift. But the fundamental problem hasn't changed at all. The engine still cannot start itself. Something external still has to throw the switch. The cart just looks different now. So next time you're at the gate, before the engines even start, take a look out the window. Find the cart. Watch how the ground crew connects the hose, communicates with the flight deck, and manages the sequence. Watch the engine begin to turn. It looks calm from where you're sitting. But what's actually happening inside that engine cowling in those first few seconds is precise, high stakes, and completely invisible to most of the people on board. You now know what they don't. That rumble you're about to feel isn't just an engine starting. It's a $30 million machine being forced into existence by a cart that nobody ever looks at. And that honestly is one of the best things about aviation. The most critical moments happen quietly, right in front of you, managed by professionals who have done this thousands of times, and almost no one on board has any idea. Now you do, and once you know it, you can't unknow it.